Hello, we are discussing about GATE 2004 ECE paper and the topic is related to electronics. In abrupt p-n junction, the doping concentrations on the p side and n side are Na acceptor concentration on p side 9 into 10 power 16 per centimeter cube and Nd 1 into 10 power 16 per centimeter cube for donor concentration to get the n side. The p-n junction is reverse biased and the total depletion width is 3 micrometers. The depletion width on p side is, so if the total depletion width is 3 micrometers, what will be the depletion width on p side? Okay. So for that one we will start like this, and we know that one a p-n junction is going to be formed whenever a p-type semiconductor is going to be added to n-type semiconductor. If you are going with p-type at that time, that is going to be called as neutral, and n-type semiconductor is also neutral. Remember that one. Extrinsic semiconductor is also neutral. Every semiconductor is neutral, whether it is p-type or n-type or intrinsic or pure semiconductor. So whenever you are adding at that time, p and n are going to be added at that time under open circuit equilibrium condition. You are going to be getting a depletion region, and depletion region is going to be consisting of only ions. So these ions are going to be, for p side it is negative ions and for n side it is positive ions. So these ions are going to be charged negatively, created negative charged ions, positive charged ions on n side, and the other side is, the region is neutral. This is also neutral. So total depletion layer width is nothing but W, and depletion layer width on p side is Wp, depletion layer width on n side is Wn. So if you observe, p and n type semiconductors are neutral, but whenever they are joined together to get a p-n junction, at that time some phenomena is going to be taking place under equilibrium condition. Even though you are not applying any voltage, at that time there will be a depletion layer is formed, and in that one positive ions will be created near the junction on n side, negative ions will be created near the junction of p side. So now if you observe charge on p side, charge on n side, we will see that one. Meanwhile you must assume that one, this is a three-dimensional view. So in this three-dimensional view, by that time this is going to be called as common area. This is area which is common for n side as well as p side. So now if you see charge on p side, excuse me, charge on p side must be equal to charge on n side in depletion region, because every recombination is going to be creating one positive ion and one negative ion in the depletion region. So number of positive ions equal to number of negative ions, that is nothing but number of negative ions. Number of negative ions equal to number of positive ions. Negative ions on p side is equal to number of positive ions on n side, because the other side on the p side is neutral. So entire p side is nothing but from this point to this point, but out of that one this region is nothing but neutral region, so no charge, and where the charge is present is nothing but due to ions. So charge on p side is nothing but number of negative ions, charge on n side is nothing but number of positive ions. Number of negative ions can be calculated as total volume charge rho Vp into volume on p side, volume of p side, and here it is total volume charge density rho Vn into volume on n side. So rho Vp implies nothing but volume charge density. We know that one p and n are going to be created with the help of number of acceptors, number of donors. If you check about the dimensions, they are centimeter per centimeter cube, that is nothing but per unit volume. Per unit volume you are going to add Na number of acceptors to get p side and Nd number of donors to get the n side. That is nothing but they are called as volume charge distributions. At most, if all the acceptors and donors are ionized, by that time you may get a maximum of Na number of volume charge density, and each ion is going to be having a charge of Q multiplied by volume is nothing but area A multiplied by width, that is nothing but Wp, whereas rho Vn is nothing but at most you may get Nd number of negative or positive ions if all the donors are ionized, and each donor is going to be, each positive ion is having a charge of Q multiplied by volume on n side is nothing but area multiplied by width on n side. So Q get cancels, AA get cancels. What you are getting is nothing but Na into Wp is equal to Nd into Wn. From this one, this is very important equation. From this one we can say like this. Case 1. If Na is equal to Nd, then Wp is equal to Wn. That is, if both sides acceptor and donor concentrations are same, then width on p side and width on n side are going to be equal. So the depletion region penetrated equally on both sides. Let us assume we are going with second case. If Na not equal to Nd, then A. If Na is very large compared to Nd, that is acceptors are more, that is nothing but p side is heavily doped, so you can say it as this is p plus n junction. By that time, from this equation 1, okay, we can say Wp is going to be very small compared to Wn, because total charge has to be same. That is nothing but depletion layer penetrates more into lightly doped side, that is on n side. So the total depletion layer width, you can say it as W is equal to Wp plus Wn, and it is approximately equal to Wn itself. So entire depletion layer width is going to be on lightly doped side only in this case. Now if you are going to say B, if Nd is very large compared to Na, by that time donor concentration is large, so it is Pn plus junction. So in that case, Wn is going to be very small compared to Wp. So here it is, total depletion layer width is going to be Wp plus Wn, which is approximately equal to Wn itself. So we can say, if the p and n sides are uniformly doped, at that time depletion layer is penetrated equally on both sides. If p side and n side are going to be unequally doped, at that time whichever is lightly doped, at that time the depletion layer is going to be more penetrated into that side. So important point is depletion layer penetrates more into lightly doped side. So now we will come towards our question. Given is acceptors is 9 into 10 power 16 and donors is 1 into 10 power 16. So here it is, Na is very large compared to Nd. So it is a nature of p plus n junction. Okay, and we know the equation Na into Wp is equal to Nd into Wn. Okay, what was given is nothing but W. W is equal to Wp plus Wn. Okay, so from this one we can write it as Wp plus Wn, and here it is depletion width on p side we must know, so that we can write Wn is equal to W minus Wp. Okay, substitute this value. Okay, otherwise Wp by Wn, from this equation Wp by Wn is equal to Nd by Na. So that is nothing but Nd is nothing but 1 into 10 power 16 divided by 9 into 10 power 16, which is 1 by 9. So Wn is equal to 9 times of Wp, and what we know is nothing but W is equal to WP plus WN. So total W is equal to WP plus WN, and W is equal to 3 micrometers, and here we are interested in WP, so we don't change WP. WP plus WN, you can write it as 9 times of WP. So 10 times of WP is 3. So WP is going to be equal to WP is equal to 0.3 micrometers. So this is WP is 0.3 micrometers. So WN will become 2.7 micrometers. So from this one also you can say the depletion layer width is going to be very small in heavily doped side. P side is heavily doped, so that the depletion layer width on P side is very small, that is 0.3 micrometers out of 3 micrometers, only 1/10th part. Okay, so the right option for us is B. Thank you.